All right. It's such an introduction. Thank you very much for the invitation. I'm going to tell you about some recent work I've been doing about generalized concepts of symmetries in particle physics. And we will start with a kind of overview of higher form symmetry, at least just to jog our memories, set some terminology. Higher form symmetry will be sort of the bedrock that we'll build off of. And we'll develop some new notions of symmetry, and we'll see how those new notions might even be relevant in particle physics. Okay, so what's the main idea of higher symmetry? The main idea is we want to develop concepts of symmetry that involve extended operators. And in this talk in particular, we want to apply that to problems relevant potentially for phenomenology. So the language that we use is one that has become standard. So a P-form global symmetry is something where the charged operators have our dimension P. So ordinary symmetries are zero-form symmetries. They act on local operators, like terms that might appear in a Lagrangian. And one-form symmetries have charged lines. Lines could act on the vacuum and create strings, for instance. Okay, two-form symmetries are also relevant in this discussion, but we probably won't talk too much about them today, so I'll skip that. And we'll often write currents. Currents for P-form symmetries are antisymmetric operators with P+1 indices. So for a one-form symmetry, which is kind of our hero today, we'll have a current J mu nu, which is antisymmetric and conserved at least at separated points. Okay, so the example to keep in mind when you're thinking about one-form symmetry is U1 gauge theory without matter. So I'll call that U1 electromagnetism or Maxwell theory. Here there are two distinct one-form symmetries. There is an electric one-form symmetry, which measures the charges of Wilson lines, and J mu nu for that is just F mu nu. And then there's a magnetic friend, which measures the magnetic charge of a 't Hooft line, and the current for that is epsilon tensor contracted with F. And so those are the currents. We could alternatively discuss the charges. The charges we would get by integrating. So we'd integrate over, in this case, we would call it Gaussian surface, measure the charge. And we learn in ordinary electromagnetism class that the answer for the charge is independent of the shape of the Gaussian surface. And that's the topological property of the charge operator that's manifesting the fact that the current is conserved. So the one nice thing about higher symmetry is that it gives you a way to think about different phases and to get sort of new symmetry-based explanations for facts that we're familiar with. For instance, you might want a symmetry-based explanation for why the photon is massless. Of course, we know since time immemorial that the photon is massless, or has at least a very stringent bound on its mass. And higher symmetry gives you a way to think about that. You can think about that by looking at this kind of matrix element here. So here's the current acting on the vacuum, and it has a non-zero overlap with a one photon state. Epsilon there is a polarization tensor. And you should compare that to the matrix element for a spontaneously broken ordinary current, which acts on the vacuum and creates a one Goldstone boson state. So the interpretation of this formula is that this one-form symmetry is spontaneously broken, and the photon is the Goldstone mode. So that's a nice symmetry-based point of view on the masslessness of the photon.
So just one question on your previous slide. So obviously, I mean, you probably say it later, but if you have charged matter, the U1 form symmetry is no longer broken.
Not this one. This one is well, there's an electric and a magnetic. So
right. So you're saying like this.
The magnetic one form symmetry will remain.
So you can claim that the photon is still the Goldstone of the magnetic unbroken, but yeah.
Okay, but anyway, let's come to the one-form symmetry breaking, which is really, applications of symmetry in symmetries in particle physics are often about trying to understand the breaking mechanism, right? We want to know, we have many approximate symmetries, we want to understand how to break them. So for an ordinary symmetry, we know what we're supposed to do. we're supposed to just add a charged operator to the Lagrangian and characterize, maybe we can organize them by dimension or something like that, looking at the leading operators that break a symmetry. But one form symmetry is more interesting because, as I emphasized before, the only no local operators are charged under a one-form symmetry. Therefore, you cannot break a one-form symmetry so easily in effective field theory. You can't just add an operator to the Lagrangian and break it. Something richer has to happen. Let me just highlight that by talking about the symmetries in Maxwell theory that we were talking about before. So let's add, for instance, the Euler-Heisenberg term, leading term, and we could reanalyze the symmetries of that now interacting theory. Well, okay, the Bianchi identity still holds. F is still locally dA. So the magnetic one-form symmetry is sort of trivially present. And the electric current gets deformed, but if you work out what the equations of motion are, you find that there's still something that can still be cast as something is conserved. So you didn't really lose any symmetry by doing this. You deformed what the current was, but the symmetries remain. And that's a manifestation of the fact that there are no local operators that you could add to the action to break this symmetry.
How come the electric one is broken when you add charge fields?
Well, that will be the next slide, but charge fields are, that's not a local operator deformation of the action. Okay, so to break one-form symmetry, you do that by having charged matter fields, and the physics underlying that is screening. So of course, if you have mobile charged particles, Gauss's law breaks. The answer to the Gaussian surface integral depends on the shape of the surface, the distance from the charge, for instance. And physically, we think about this using this picture of screening or the Uhling potential. We try to write down an effective charge Q that depends on the distance R from the source. So Q here is like some infinite mass Wilson line insertion. And now Q depends on R, and at one loop you can work out this this formula which characterizes that. So that log is the signature beta function. And the fact that Q depends on R, if we think about it in terms of one-form symmetry, is a statement that the symmetry is broken. The one-form symmetry is broken. We used to have a charge Q that was independent of the distance that we measured it at. Now it depends on how we measure it. Okay, so let me just wrap up this sort of introductory part of the talk. I mean, one-form symmetry is really ubiquitous in gauge theory. I talked about the Maxwell example because it's the simplest. But SUN Yang-Mills also has a discrete one-form symmetry that measures Wilson line charges. And again, this makes precise the physics of screening. It allows us to sharply distinguish various phases of gauge theories like Higgs versus confinement. And most of the early applications of higher form symmetries have focused on something like that, have focused on characterizing phases of quantum field theories or detecting anomalies. And we're going to do something a little bit different. We're going to focus on patterns of symmetries in effective field theories, and we're going to see some kind of interplay between ordinary and higher form symmetries. So that's where I'm going next. Any questions about this part? Okay, so one possible generalization that we could talk about of higher form symmetry is what's called higher group global symmetry. And the basic theme here is that when a quantum field theory has higher symmetries of different degrees, different P's, so say a 0 form and 1 form symmetry, then they need not factorize. They could form some interesting mixture. So let's try to analyze with an open mind, what is the symmetry of U1 gauge theory, but not just with no matter. Now we'll have some massless fermions of charge Q. Okay. What could be easier? So we have two sort of obvious symmetries. We have this 0 form symmetry, the SUNF left and SUNF right. It's an ordinary symmetry that rotates the fermions. We get two of them because it's massless. And then we have a 1 form magnetic symmetry because there's no dynamical magnetic matter in this problem. We don't have the electric symmetry anymore because we have charged electric matter. And we can ask, are these symmetries factorized or are they mixed in some way? And the answer is that they are mixed. How can we find the mixing? Well, the thing to do is to look at the 3-point function of currents. So in particular, this 3-point function, we have 2 ordinary currents chosen from up here, and one form current, J with 2 indices chosen from here. And you should think that what I'm doing is something analogous to looking for the structure constants of a non-abelian global symmetry, which you would find by looking at the 3-point function of ordinary currents. So I'm doing something analogous, but I'm allowing the currents to have different kinds of indices. Okay, so what kind of structure do you find here? You find some interesting ward identities. It's convenient to organize these ward identities at a special locus in momentum space, something that is familiar from older literature on similar subject. So we'll look at this 3-point function, for instance, depends on 2 different momenta, and we'll choose the momenta to be related in that way. And okay, so what we find is a ward identity relating a 2-point function of the one-form current. That's up here. So there's some tensor, there's some 1 over p squared, and there's some structure function f. And then we look at this 3-point function that I was advertising before. And okay, there's a different tensor, which has some fixed canonical form that I'm not writing. There's again a 1 over p squared. There's some group theory indices k and l. And then there's again the same structure function. That's the ward identity. The fact that the same structure function is appearing in both correlation functions. And a hero in these ward identities is this number kappa. So QED realizes this with kappa equal Q, and J, either of these chiral symmetries, and the one-form current, the magnetic one-form symmetry that we were talking about before. This kappa is something like the structure constant of this algebra. You can compare kappa to something like Fijk in a Lie algebra. It's also quantized. We can also, if we wanted to say these ward entities in terms of an operator product expansion.
This doesn't have a lot of content until you've told us what the tensor prime is.
Yes, you can look up
the quantization. I mean, why not just absorb kappa into tensor prime?
Well, the only reason for not writing tensor prime on the screen, Greg, is because it would be too distracting. But it's not that the tensor is unknown, it's completely fixed. I just haven't written it here. Right, so you could also characterize these ward identities in terms of an operator product expansion. And here's the operator product expansion. So we have the divergence of this current. Usually the current is conserved, but what we mean by that is it's conserved at separated points. When we look at coincident points, we might find an interesting contact term. And here we find one. The divergence of this current when it touches another current has a contact term controlled by kappa. There's a derivative of a delta function, and then there's our one-form current popping up there again. So that's the operator product expansion that we're trying to characterize. Yes,
What is Q?
Q was the charge of the electrons in this problem. So the electrons have all uniform charge Q. Q could be 1. More questions?
Your OP could have been written as a more conventional OP without the d mu of J mu.
Yes, but then I would have had to.
You would have found the singular term, which would sort of be the minimal solution of the equation you said.
Yes. So you might ask, how do we summarize what we're talking about in a weakly coupled gauge theory? We're talking about something sort of similar to anomalies, but slightly different. So let's look at in a weakly coupled gauge theory where we can characterize various phenomena using triangle diagrams. And the meaning of these triangle diagrams depends on who lives at the vertices. So if the 3 vertices are gauged, so GGG, then that's just an ordinary gauge anomaly, and this theory is not consistent, so we won't study it further. The other end of the spectrum, if they're flavor, that's an 't Hooft anomaly. It's an obstruction to gauging, something that matches along flows. And we're somewhere in the middle here in this talk. So there are two other possibilities, GGF. Usually you would say that's the Adler-Bell-Jaquev anomaly. The flavor symmetry is broken quantum mechanically, although let me put a big maybe there for the next part of the talk. There'll be something interesting that we'll talk about there. Instead, we can also talk about the GFF triangles. That's where the flavor symmetry remains, but it forms a non-trivial current algebra with the magnetic one-form symmetry. So that's what we're talking about here. Okay, so I've told you the structure, but what can you do with it? Well, there are some interesting things that you can do with it if you're thinking about patterns of symmetry emergence along RG flows. That's one of the applications. So the basic observation that you should take from that Ward identity is not any of the details, but just this kind of essential fact that the collision of two ordinary currents can make the one-form current with a quantized coefficient kappa there. So the fact that it can make it is scale invariant because kappa is quantized. So I've highlighted this fact. So for kappa not equal 0, the flavor symmetry generates the one-form symmetry. And this is interesting to think about when both symmetries are accidental or emergent in the infrared of the renormalization group flow. So we could imagine, here's a diagram in energy. So here's our infrared. It's an effective field theory. It has some flavor symmetry and some magnetic one-form symmetry. You could think it's an abelian gauge theory. Later, we'll think it's the standard model with the one-form symmetry being the hypercharged gauge group. And here's some UV theory without the flavor symmetry or the magnetic one-form symmetry. So we're imagining both of these symmetries are emergent. That could, of course, happen. And then we can identify two scales. These are the scales in our effective field theory where, say, the one-form symmetry becomes an approximate symmetry below this scale, and here's a scale where the flavor symmetry becomes an approximate symmetry. And because of this operator product expansion, we get an inequality here. Once the flavor symmetry has emerged, the one-form symmetry must already be there because we can make it by colliding two currents.
So could they be parametrically separated or the factor of pi be enough? Or?
A pi is okay. These are approximate notions. Yeah.
What about 1/pi?
I think what I really mean is that you cannot have, if you want a rigorous statement, is that you cannot have the reverse be true parametrically. Okay, so you could think of, let's try to apply this in, again, our QED example, but now viewed as sort of a toy model of unification. So we'll now think of our QED as the infrared. It had a one-form symmetry, the magnetic one-form symmetry, and it also had two flavor symmetries, the SUN left and SUN right. And these have kappa equals plus or minus 1, and the diagonal has kappa equals 0. And so what we learned from this, the previous slide, is any UV where the U1 gauge group, where the magnetic symmetry emerges, say via Higgsing, must necessarily break some of this flavor symmetry. That's what we learned. So you could try it in the most obvious way. You could try to unify, say, these chi plus and chi minus, these charged fields into a doublet of SU2. Of course, if you do that, you will break the left and right flavor rotation separately, but preserve the diagonal, which is the thing you're allowed to do because the diagonal has kappa equals 0. And a key point for richer applications that are coming in a moment is that within weakly coupled gauge theory, the allowed UV flavor symmetry is an important thing. It tells us which IR fermions can be unified into UV gauge multiplets. So that's why we're so interested to know what flavor symmetry is around.
Can you step back? Can you explain this sentence again?
The bottom one.
Yeah.
Yeah. So can there be a model, for instance, that unifies chi plus and chi minus? Well, let's do one of them separately. Can there be a UV model that keeps chi plus all on its own without unifying into chi minus? Keeps, say, the flavor symmetry rotating chi plus. And the answer is no, because of this. So this tells us we could not have a UV gauge model, no matter how complicated, where chi plus and chi minus remained separated and there were flavor symmetries acting on them individually. That would not be allowed.
What if one of them is a composite and the other is something?
I'm working here, I'm imagining weak coupling for
So this is taken within weakly coupled field.
within weakly, I'm applying it within weakly coupled so that I can.
Because there are examples with duality that one of them is a composite and the other is elementary.
Yeah, so the statement that I said here, I mean, this will still hold. So this pattern of flavor symmetry will still hold, but the language of unifying into gauge multiplets, that's a language of weak coupling. Okay, often we're interested in applying these kind of ideas when we have approximate symmetries. So imagine we have an approximate symmetry, a flavor symmetry F, which is broken by Yukawa coupling. What can we say? Well, now we'll have to be careful because there could be additional contributions to the triangles, these GFF triangles that I was highlighting, from matter which is massive, but whose masses go to zero parametrically as I restore the symmetry, as YF goes to zero. So these additional matter fields would allow us to preserve this flavor symmetry in the UV, but if YF is small, they're parametrically lighter than the unification scale. So we will now have a diagram that looks like this. So if here's again energy space. Here's our infrared with some flavor symmetry F. Now here's a UV where we want to preserve this flavor symmetry, and kappa is non-zero. And we need to, in order to preserve this flavor symmetry F in the UV, we need kappa to go away. We can add some matter here because this symmetry is approximate, but that matter has to be suppressed from the UV Higgsing scale by this power of the Yukawa coupling. So that's how to think about this in a sort of sporion-like way. Okay, so let's do it for real now. Let's try to do it in the standard model. So the standard model flavor symmetry for each of the fermion species is violated by the Yukawa couplings. Let's temporarily turn off the Yukawa couplings and analyze multiplets there. So when the Yukawa couplings are zero, we just have these big SU3 symmetries rotating each of the fermion types separately. And each of these flavor symmetries has a non-zero FFG coefficient, kappa. So here are the FFG coefficients, where the the magnetic one-form symmetry in question is, of course, coming from hypercharge. So the standard model has this approximate two-group global symmetry broken by the Yukawa couplings. And this will be useful to understand the possible structure of gut models by constraining their flavor symmetries. And as I have emphasized, since we're talking about weakly coupled gut models, this is about telling us about which standard model fermions can be, in principle, be fused into gut multiplets. So here by gut, what do I mean? I mean any model where U1Y emerges from something non-abelian. So the magnetic one-form symmetry is broken. Could be many factor gauge group, could even have abelian pieces, just as long as U1Y itself is not there in the UV. And the allowed UV flavor symmetries in any such model are diagonal combinations of the flavor symmetries that I had on the previous slide, those SU3s rotating each of the fermions individually, but they're diagonal combinations with total vanishing kappa. They're the analog of the diagonal in the QED example. And so here's a little table over here of which combinations have vanishing kappa. They're organized by how many of the standard model fermions do they act on. So if you want them to act on, say, just one standard model fermion like Q or L, then there are none. So there's no way to put those into gut multiplets on their own, keeping those flavor symmetries, which is something that is very familiar from anybody who's tried their hand at gut model building. Now, if you combine, if you look at diagonal combinations that act on 2, 3, 4, or 5, you'll find some possibilities. So there are several that act on 2 fermions, several that act on 3, none that act on 4, and one that acts on 5. And this is familiar in examples of guts. So for instance, in SO10, all the standard model fermions plus a friendly right-handed neutrino are unified into a single multiplet here. And so that has only the flavor symmetry that is the diagonal combination that acts on all 5 together. That's this combination right there. SU5 has 2 multiplets, the 5 bar and the 10. So that's choosing a 2 and a 3. And Padi Salam has this combination here, another 2 and a 3 if you add the right-handed neutrino. So familiar examples are, of course, realizing the things that are implied by consistency. But this is also, this organizing principle works for guts that have yet to be written down for huge product gauge groups if you're interested. So I mentioned approximate symmetry. Where does that approximate symmetry come to bear? So one place is if you try to look at models of trinification. So another gut that people have been interested in before is this one where the gauge group is SU3 times SU3 times SU3. And the fermions are in this pattern here. And now here, D prime and D bar prime are an extra pair of vector-like down quarks needed to fill out the representations. And if you look at these flavor symmetries that could be there, you think that this is an illegal pattern. It's not one that appeared on my list. And this is exactly possible because of the fact that without interactions, without Yukawas, this does not reproduce the standard model spectrum. And this theorem that I was giving you about what happens when you take into account the fact that the Yukawas break the flavor symmetry is at play here. So what happens is that the same interaction, which is needed to lift the this extra vector-like pair of down quarks, is also the interaction that generates the Yukawa couplings. That's what's guaranteed by this general result, is that these two interactions will be tied together. Okay, that's one application of higher symmetry in particle physics. Are there any questions about this?
Could you go through the basic reasoning again? If kappa is non-zero, you have some restriction on what representations can be unified, and then at some point you said that kappa, you wanted to arrange that kappa was equal to 0, and then I got lost.
Yeah, so let's go through this example.
I think it's the key point there. Yeah.
Yeah. So because if we fuse 2 ordinary currents, it makes the higher current with coefficient kappa. If we break the higher current, we must also break the ordinary currents. That's the first point.
Okay.
Okay. So so now we're trying to ask, can we unify, for instance, can we find in this toy model, could we find some non-abelian gauge theory where U1G, this U1 here is some piece of the non-abelian gauge group, and say chi plus and chi minus are in separate multiplets maintaining their separate flavor symmetry, one acting on chi plus, the other acting on chi minus. That's the thing that is excluded by this.
And why is that excluded?
Because in the UV,
This
we
is
will-
excluded when kappa is not 0, right?
yeah, exactly. Yeah, because in the UV, the magnetic one-form symmetry is broken.
Right.
Therefore, flavor symmetry is broken.
I see. Okay.
We assume that the various SU3s are exact in the unified theory. In other words, do you assume that if you set all the Yukawa couples to 0, and you had all these products of SU3s, which act on the 3 different generations, do you assume that these SU3s still work in the gut?
I'm asking if it's even possible for them to work in the gut.
Let's assume they don't. The way these guys are organized in the UV is completely different.
Yes, so I'm excluding. I'm sort of studying the opposite problem. I'm studying when it is possible to even have those flavor symmetries at all.
There are examples of unified theories with more massive multiplets. So that the SU3, so the different multiplets do not come from the same multiplet of ground unification at high energies.
Yes.
So then you won't have these SU3s are not going to give you this control.
In that example, these will not give me this control. I can run this argument for subgroups though. I'm not doing it on the board, but I can run it for subgroups if I want.
But so you see what I mean? Like,
Yeah, I understand what you're saying. You can have some mix, some family unification or something like that.
but even without it, it's just that the 3 upwards and the 3, say,
They're split, yeah,
downwards
I understand.
do not come from the same multiplet at high energies.
Yeah, I understand what you're saying. Yes, I am looking at a restricted class right now, but you can play this game with any sort of pattern, any possible sub also.
So in that table, previous slide, yeah, so you have this table of, all the ways you can organize the standard model multiplets. And the examples you've given, are there any combinations I could consider for which we don't know I got?
Yes, there are. Maybe let's talk about it afterwards. But yeah. It's an interesting thing to understand if that meant we were missing a really elementary possibility, or if there's some constraint I didn't figure out. Okay, so let me move on now to non-invertible chiral symmetry, a kind of different generalization of higher form global symmetry and some of its applications in particle physics. Okay, so chiral symmetry and massless QED. This is a plot of me in time. I want to emphasize that it is of me. I will explain momentarily. So previously we were talking. We're always talking about QED in this talk. Basically, previously we were talking about multi-flavor QED and what's the symmetry of multi-flavor QED. Let's go back to single-flavor QED. What's the symmetry of single-flavor QED? Okay, so there's the vector-like current, which is gauged. And then there's the classical chiral symmetry. I'll give that current the name J mu, and it has an ABJ type anomaly. That's the triangle with vertex flavor gauge, which leads to this equation. Divergence of J is epsilon FF. So you should ask yourself this question: does J generate a conserved charge? That's the question on this slide. And there are various possible answers depending on your degree of sophistication. So, before you learn about anomalies, you just learn classical physics and you think, yes, it's definitely a symmetry because there's a symmetry of the action, it looks like. So that's me in this stage. And then later you learn about this triangle and you think, well, no, there's no symmetry because the current is not conserved. So now you've reached this kind of mid-width evolution, and then there's Tuft. Tuft, I think, is the one. Maybe there are others. Not able. Maybe no. There's another possible answer, which is that even taking into account this equation, the answer is yes. And what's the reason? Well, if you try to integrate this equation to determine what is the total violation of the chiral charge, Q of plus time equals plus infinity minus Q equals of time equals minus infinity, you'll find that, let's say we do that integral on S4, like a regulated R4, that integral is 0. Because this is sourced by abelian instantons, and there just are no abelian instantons in that simple configuration. So for instance, like at the level of the S matrix, this actually is a symmetry. A very well known one. Okay, so that's the answer, that's yes. So there's clearly something going on. There's still some selection rule. There's still something like a symmetry, but we can't formulate it in the sort of standard way of looking at this current. We have to do something more sophisticated. So I'm going to tell you what you have to do first, and then we're going to study that symmetry. Okay, so the kind of question that we're asking here is, can we make sense of the ABJ anomaly, that equation, divergence of J is F wedge F? Can we make sense of that equation non-perturbatively? Or is that something that only has a meaning in perturbation theory? And then the first idea is we're going to give up trying to find a current. That seems to be more or less hopeless as far as I can tell. We're not going to do that. Instead, we're going to work with an exponentiated charge. And we'll see that we can, although that just sounds like a linguistic change, we'll see that we can make progress on that. So if you want to make the exponentiated charge, without the anomaly, this is trivial. So you just take the integral of star j. J is has one index, so star j is like a 3 form. We integrate it with some phase over a 3 manifold where we want to define the charge. You could think that M3 is like all of space. So here's this operator. This is the 3 manifold. Now, with the anomaly, that doesn't really work because the current is not conserved. That operator is not topological anymore. But what should you try to do? Well, you could try to do something that, I don't know who was the first to attempt this trick, but you can even read about it in Weinberg. You just say, let me move the divergence to the other side. Divergence of J is F wedge F. Let me just put the antiderivative of F wedge F on the other side and call that part of J. Okay? So you might want to integrate this formal current. Star J minus 1 over 8 pi squared A wedge F. This is an old idea, but it's not really correct because A wedge F is not gauge invariant. That doesn't really quite make sense. But there's actually a kernel of an idea there. So if you go back to, if you forget about the current, let's try to exponentiate it. Look at what kind of mistake we're making if we try to exponentiate that. So we have this star J piece that we understand. Then we have this A wedge F piece. And we have alpha, we're trying to do a general rotation by angle alpha, and we have some pi's. And the problematic term is this, and it looks like a Chern-Simons term, but a Chern-Simons term with the wrong level. What's the level? Well, the level is alpha, this angle, over 2 pi. That's the level. Okay, what levels can we make sense of? Well, we can definitely make sense of integer levels. Okay, so we could make sense of alpha equals 2 pi times an integer. That wouldn't be very good though, because that's like doing no rotation at all. So we need something a little more creative than that. But we can also make sense of a fractional level, not as a classical term on its own, but as a response, as the answer to a partition function. So that's what's on the bottom of the slide here. So this fractional level, where alpha is 2 pi over k for integer k, is well defined as a response to a so-called fractional quantum Hall state. And the way to think about that in kind of field theory language is we're going to introduce a new Chern-Simons field, C mu. This field does not live in the bulk. It lives only where we're trying to define this charge, only on M3. And I'm going to have a functional integral dc. And I have this Chern-Simons term for C with level k. This k is the same as this k. And this whole thing is coupled to the gauge field A through this off-diagonal Chern-Simons coupling. Now, if you squint and complete the square, just integrate out C and complete the square, that would generate this, this A wedge F term with this fractional level that you want. That doesn't make sense in general to do in a general topology and general insertions of other operators, but this expression does. So this will be the definition of our operator. Yes.
I think you have a typo.
You need alpha in the first factor?
Oh, yes, this is a typo. Yeah, was that your question too, Greg? Yeah. This is-
Yes, that's what I was pointing out.
Yeah, this is wrong. Sorry, there should be no I alpha there. Thank you. Yeah.
It's important here that alpha is 2 pi over k instead of 2 pi times k prime. Okay.
No, more generally, you could do this for any rational, any 2 pi rational. I've just given you the simplest one. The theory that you will need there depends on what rational number you choose. That's a kind of unusual feature. So we're sort of adjusting the definition of the operator depending on k or on the rational there.
Moreover, you'll have to introduce a non-trivial K matrix for general rational.
There can be choices if it gets richer. Yes.
If you have alpha's 2 pi times a general rational number, you'll have to introduce a K matrix.
Yes. Yes. Okay, so this, what are the features? So this gives an intrinsic definition of the symmetry, this chiral symmetry, that had an abelian ABJ anomaly. So that was our first task. We gave some operator-like definition of it that makes sense without referring to weak coupling. So it acts on local operators as a chiral rotation. So for instance, it forbids the mass term, the fermion mass term. So it acts in the standard way, as was expected. Remember, this whole business was started by saying, well, it looks like there's a chiral symmetry still. So here I'm telling you, yeah, there kind of is. But it acts unusually on 't Hooft lines. So where you start to see some funny business at this kind of symmetry is when you act it on non-local operators. So for instance, if we have an 't Hooft loop, and here's our charge, if we sweep this operator past this 't Hooft loop, it turns it into a kind of open surface operator. So what's on this blue here is this topological surface, which is the exponentiated integral of f. That was the one form current. And one of the basic points, why are we seeing something interesting when we do that? Kind of intuitively, what you should think is, once you start having 't Hooft lines, you start having non-trivial f in the game. And we had the equation divergence of j is f which f. So once you have f on by an operator insertion, you're going to see some remnant of the anomaly. That's what we're seeing here. And you should think that this is analogous. This picture is just like a higher dimensional uplift of the order disorder map that comes from Kramer's Wannier duality.
The edge modes of this Chern-Simons theory are going to carry energy momentum. So are you adding extra physical degrees of freedom because of the edge modes of the Chern-Simons theory?
Adding physical degree, they don't carry bulk energy momentum.
No, but they're edge modes. The Simons theory would have an edge mode. I don't know, maybe they're out at infinity and you don't care, but.
You mean, well, let's make it more physical. Let's put it on a finite edge. Yes, I would say that there's something gapless there.
So you're changing the theory, you're adding some new dynamical degrees of freedom.
I don't know if I'm changing the theory. I'm saying that this theory has a defect, and at the edge of this defect is something gapless. That can happen quite often. Juan, you also you also asked about clarifying the last comment. What I meant is that if you look, for instance, at the critical Ising model in 2 dimensions, the Ising model has a Z2 symmetry, but also an additional Kramer's Wannier duality symmetry, because it is self-dual under Kramer's Wannier duality if you sit at the critical temperature. And if you take a local operator across this duality, it will now be a line, this object. It will come out as a disorder operator, so a point operator with a topological line attached to that. So what I'm saying is that picture has been uplifted to this one here. Okay, so we're seeing some price for the ABJ anomaly. We saw this interesting action on the 't Hooft lines. Here's a price for introducing, another price is that we have some interesting fusion algebra, something different than we might have naively expected. So let's call D this non-invertible chiral symmetry operator, and D bar something like its adjoint, trying to make an adjoint at least. So conjugating it with CPT. And if we collide them, we get this expression on the right. So this is a sum over surface operators. It's sometimes called a condensation operator, studied, for instance, by Sahan. It's a sum of magnetic flux operators. These are the magnetic one-form symmetry. If you act this equation on local operators, the local operators don't see F. So on the local operators, this is just like saying D bar is 1. Which is fine, that's what we expected. On local operators, it's acting like the chiral symmetry. The chiral symmetry looks unitary on the local operators. But if you look at configurations where F is non-trivial with magnetic charge, then that's not the case anymore. In fact, this can even be 0. So this is a kind of new algebraic notion of symmetry. It's beyond groups, the kind of structure that we're finding here. So these elements don't in general have inverses, hence why people call them non-invertible. Okay, so in the last 15 minutes, 10 minutes, I'll tell you about how to use these in some models of particle physics, how to think about them, and maybe also how to organize previously observed phenomena in a kind of symmetry-based language. And as I stressed before, when you're thinking about applications in particle physics, what you want to think about is symmetry breaking effects. Okay, so this is similar in spirit to what we had before. The chiral symmetry is with an abelian ABJ anomaly is in some kind of algebra with the magnetic charge, which is a one-form symmetry. And if you have dynamical magnetic monopoles, that will break the one-form symmetry. The magnetic version of this stringing effect that we talked about before. And via this algebra that we have just talked about, that will get communicated to a violation of the chiral symmetry. So coefficients of operators violating non-invertible symmetry will be protected from large corrections in flows where this chiral symmetry is an approximate symmetry of the infrared. And dynamical magnetic charges at a higher scale will break this chiral symmetry. That's what we're going to see in examples. Now, you might try to estimate what's going on here, just qualitatively. I'm talking about, say, a virtual loop of monopoles, breaking a one-form symmetry and then breaking this zero-form symmetry. Let's try to estimate the size of this. And I'd also point out a very nice paper by Fan, Fraser, Rees, and Stout about similar phenomena. So imagine your monopole comes from a Higgsing at some higher scale. Let's say V is the Higgsing scale and G is some UV gauge coupling. So then the monopole mass is V over G. And there's a short distance cutoff, which is like the W boson mass, V times G. And so if you had a loop of monopole, and you looked in a one particle formalism, what is the size of this loop? It's e to the minus s. We try to estimate, well, that's like e to the minus mass times the short time that it propagates, which is e to the minus some number over G squared. So loops of monopoles, kind of not unexpectedly, will violate chiral symmetry non-perturbatively. That's going to be the size of the effect we can expect. And another point is that you should recognize that e to the minus 1 over G squared as a kind of hallmark of an instanton contribution. And indeed, that is what's happening. So you can have these monopole loops. This is giving kind of infrared affected field theory of UV instantons. And that should be expected. So if we have this ABJ anomaly where we had divergence of J is epsilon FF, if we upgrade, if our U1 gauge field comes from the UV via Higgsing, if we upgrade it to this equation, now we can't save it by any tricks. Now we can't save the chiral symmetry anymore. Trace F wedge F. There really are instantons on S4 that will violate that symmetry. Yes.
Perhaps it's equivalent, but if you take your space-time to be a non-commutative space, then there are also instantons for U1.
By the state operator correspondence, can you change the that to an insertion of extended Tuft lines?
I haven't thought about that, but that it's known that on the non-commutative space, there are instantons of U1.
Yeah, I mean, a related thing, maybe even simpler, is you could say, well, what if I did this on S2 times S2? Then there are a billion instantons.
Then they're not localized. They're not small instantons. So you could say, okay, if you make the S2 big, then the effect is suppressed. What I was saying is about R4, they are localized instantons. Whose size can be small. The non-commutativity regularizes the singularity of the instanton.
Okay, I haven't thought about that, but yeah.
So these dynamical monopoles, are you assuming that, are these a Polyakov monopoles? Are you assuming there's a unification? So that you
I'm not doing, I'm trying to match an infrared effect, which is, you know, if you had some massive soliton that, or some massive particle that you augmented your U1 gauge theory by, which is a heavy monopole, and you wanted to know what kind of effects do you get when that runs in loops. I'm estimating the size of those.
Yeah, sure. No, I understand that, but I mean, I'm just trying to understand in your story, where are these dynamical monopoles coming from? And I'm asking, is it a Polyakov monopole?
Yeah, so when I do it concretely, I will get them from some Polyakov monopole of the UV gauge theory. But I guess what
So
I'm
there's
trying to
some brand of unification that's breaking down to it.
or more generally, and not necessarily gut. I guess what I'm trying to emphasize is that the fact that loops of monopoles violate chiral symmetry is something that an infrared person can tell. We don't have to commit ourselves to a particular UV completion to understand that.
So going back to your previous slide, I mean, I don't remember the details off the top of my head, but there are papers, I think, maybe you remember better, sort of like in the 2000s, where people try to write down models for, like, you know, neutrino masses, you know, creating a mass that was like exponentially suppressed. And I think, you know, a lot of those models.
You mean like the string models one?
Yeah, like deep brain models where, like, there was a non-perturbative, only a non-perturbative breaking of the chiral symmetry. So I guess you could say that it's more in the context of this UV instanton sort of, you know, version. And
well, but if it's extra dimensional, like that's why I brought up the point that we don't have to commit ourselves to a particular UV completion to recognize that dynamical magnetic charges will dynamically break the chiral symmetry and estimate the size of that effect. It's because we could be doing it in the context of some kind of conservative 4D physics where the U1 gets embedded in some non-abelian group and we upgrade the ABJ anomaly. Or we could, like those string models, be thinking about some extra dimensional context where we have D branes and we might not have a direct field theory interpretation of it. But the symmetry based organization allows us to cover both possibilities in one go.
Will you say what you were going to say about S2 times S2? How the effect?
Sure. What I was going to say about S2 times S2 was that, you know, in that case, you would say, well, F wedge F can be turned off there. S2 times S2 is like an insertion of Tuft lines. Right? You can think that whenever you have in a Tuft line, you can excise this neighborhood and you have made a linking two sphere. So you can trade the topology of space-time, those kind of two cycles, for networks of extended operators. It's like a generalization of the state operator correspondence to extended operators. So the fact that, you know, the fact that I see something when in particular effects when I turn on, when I have configurations of Tuft lines, I could trade that for the space-time topology. Okay, let's keep going. So where are we going? We want to protect some physical effect. We want to use this to make real exponential hierarchies. What are we going to do? We're going to protect some physical effect by a symmetry that has an abelian ABJ anomaly. And then we're going to embed in some UV with monopoles to generate natural exponential corrections. That's our idea. Okay. So for instance, a elementary toy example, we take SU2. This is the UV, SU2 with two vial doublets. the Bell doublets are chi1 and chi2, and an adjoint Higgs field phi. The adjoint Higgs can condense and send us to U1, and now we'll have 2 electron flavors coming from our 2 doublets. And the infrared has a non-invertible chiral symmetry, which is violated by the UV. And that means that the UV Toph vertex will generate a very small quadratic term for these fermions. And the nice part about this is that we didn't have to put in any small numbers by hand. We generated them by an exponential. Kind of oldest and best way to get small numbers. Okay, so last few minutes, let's actually do this. Try to do this for something maybe relevant for particle physics. Let's look at neutrino masses. Okay, so neutrino masses are one of the sharpest signals that we have of beyond the standard model physics. Just to jog your memory about some of the numbers, we know, roughly speaking, some splittings, mass splittings of the neutrino species, and we also know bound on the total sum. So they can't be too far separated. And there are paradigmatically 2 kinds of neutrino masses that one could talk about. One is the Majorana mass. So here we don't introduce any new particles. We can generate a Majorana mass from this dimension 5 operator, sometimes called the Weinberg operator. And since it is dimension 5, it naturally comes with a scale. And the smallness of the Majorana neutrino masses could of the neutrino masses, if this was the scenario, could be interpreted as a statement about that scale. Dirac masses, pure Dirac masses for neutrinos are somewhat more challenging from an effective field theory point of view. Here we're going to introduce new right-handed neutrinos. I'll call them N. And now these new right-handed neutrinos are going to get masses through the Higgs mechanism, just like other lepton fields. So we'll have this kind of coupling here with Y some Yukawa matrix. And now we have a kind of challenge, which we have a new tiny dimensionless coupling in our problem. So the ratio of, say, Y nu to Y tau is like 10 to the minus 11. So that's a number, like many other numbers in particle physics, that we would like to explain somehow. And I'll try to give an explanation for that 10 to the minus 11 using the mechanisms that I have discussed so far. So I'll be kind of fast, but I'm happy to talk more about it. So what we're going to do is we're going to consider a model where we have a new U1 gauge field, so-called Z prime. This Z prime will couple to lepton family differences. So in the standard model, what are the U1 symmetries that you might try to gauge? There's U1 B minus L, but there's also L mu minus L tau and LE minus L mu. Those are allowed anomaly-free symmetries that we could gauge. So we, to give you an example, the least phenomenologically constrained, as far as I'm aware of, is L mu minus L tau. That's heavier. So we'll have a Z prime that gauges L mu minus L tau. And classically, and in this standard model augmented by Z prime, you can ignore this column for a minute and come back to it. In this standard model augmented by Z prime, there are a variety of symmetries to discuss. So there's the standard model lepton number. I'll call that L tilde. And then there's kind of the total lepton number, which is the standard model lepton number. And then you subtract off, say, the right-handed neutrino number. And the total lepton number, or at least an anomaly-free part of it, Z3L, forbids Majorana masses. And the standard model lepton number, Z3L tilde, which is also a symmetry, forbids Dirac masses. So these two Z3s keep neutrinos, these two symmetries keep neutrinos exactly massless in such a model. All very well known. Now, this Z3 L tilde, remember L tilde was the standard model lepton number. Z3 L tilde, which forbids Dirac masses, has an FGG anomaly with my new Z prime, with L mu minus L tau. So this Z3 L tilde is now a non-invertible chiral symmetry. Not a whole U1 of it, but a little small non-invertible chiral symmetry. So that allows us to anticipate universally in a kind of model independent way an ultraviolet, where as long as you have dynamical magnetic charges, you will generate Dirac neutrino masses that are exponentially small. That's something that we get directly from this symmetry. Okay, and now you might ask me, okay, let me actually put something on it. Yeah.
What exactly do you assume about the short distance theory? You assume that the non-invertible symmetry is there?
I only have to assume that it is a symmetry of the. I assume the no, it's going to be broken.
So you assume nothing.
Yeah, it's going to be
I didn't
generated.
know that you don't have some other instantons that violate these anomalous symmetries, short distances.
Other instantons. Well, I'm writing the instantons.
But the symmetries could be embedded in something else, and there could be some, right? There's no old-fashioned symmetry that forbids it. There wouldn't be old-fashioned symmetry violated by FGG anomaly. So strictly speaking, there's no such thing. How do you know there's no other FGG type anomaly that can be activated with regular instantons?
How do I know that there's not some other FGG type anomaly? Well, I guess that question makes sense in the abstract, but if I just write for you a Lagrangian that manifests the effect, then I think the question might go away. I'm just going to write for you an explicit Lagrangian where all the operators below some high scaling dimension respect this symmetry, and the instantons generate a small violation.
I think you're saying this is the kind of, there's a minimum estimate size for the size of the symmetry violation, which you might reasonably expect to get. And of course, specific UV models might also break the symmetry more. But it's not hard to arrange them to break them about this much.
Yeah, that's.
But it's very easy to add stuff to UV. Sure, it will completely mess it up.
Well, not in a renormalizable way. Well, not in say this example. And not if I commit myself to a particular theory, I can analyze what the operator content is.
You can add more stuff that will make the beta function run differently. Then at very high energies, all these gauge couplings and all these small instantons are very important. And they can lead to terms in the Lagrangian that completely mess it up. It's not the standard. What you're doing is not the standard. You do not follow the standard Wilsonian rules. Because you use a symmetry which is not really there.
Okay, let me finish this and then let's keep talking. Okay, so a simple possibility realizing this is to embed this U1 mu minus tau into an SU3 family symmetry, an SU3H, which is Higgs at some scale V phi, and that's where you should pay attention to this other column here. So here's how the leptons get grouped into multiplets under SU3H. Very simple. And the other gauge groups in the standard model come for the ride. And now each 3 and 3 bar has one zero mode. So I can write in a Topf vertex. So the Topf vertex looks like this. This is not yet a Dirac neutrino mass. So there's some exponential suppression. Alpha H is the standard gauge coupling constant. There's a Higgsing scale, and these are the fermion fields. It's not yet a mass, but I can combine it with the lepton Yukawa to get a Dirac neutrino mass. So we end up with this kind of coupling. So it's proportional to y tau, has an exponential suppression and a Dirac neutrino mass. And so you can think this is the composite interaction. There's some blob that's like an instanton, and then there's one vertex exchange.
I think Nati's statement here would be you could add like a ton of matter just to make alpha H big at the scale where this Higgsing happens. And so the effect is really big. I mean, this is a very standard thing in model building. People use up and down to make effects big or small, whatever size they like.
Yes, I could change what alpha H is. That's true. Yes.
And you don't know from the IR what the size. So you just have
No,
to.
absolutely not. I don't know. I don't know from the IR. On the other hand, if you just take some standard weakly coupled gauge theory, you might get this to be even too small. Okay, so to conclude, if you want to really do some physics with this, well, what I just told you was that the Higgsing scale from SU3H down to U1, we might want to run that down to the mass of the Z prime. Get some formulas you could take to the bank. So here's what you would get if you ran that down to the mass of the Z prime. Of course, here I'm assuming this minimal matter that I wrote down, but this is what you would get. So you would get a formula relating this Higgsing scale V phi to mz prime, alpha of Z prime, and other quantities that are known. So you could turn it around. You could say, if you were to say measure the Z prime mass and its coupling, you would, as a consequence of this simple minimal model, determine what the UV Higgsing scale would be. So to put some numbers on it, for M, it may be interesting at fairly lowish scales and strong couplings. So that's an example that I wrote there. And now maybe others are interested in asking me about the texture. I only told you about sort of an overall scale in the neutrino mass matrix, but I didn't also tell you how to Higgs. I didn't tell you anything about this Higgsing sector that takes you from SU3H to U1 V minus tau and then back down to the standard model. And that pattern of Higgs fields, in fact, people in neutrino physics have used those kind of Higgs fields to generate any sort of texture that you like, basically, or at least a broad class of textures. The only thing that I'm doing here, you could think that the neutrino problem is factorized into two pieces in my discussion. One is the texture, which I'm not discussing at all. And the second is an overall scale, an overall small size. And what I'm telling you is a kind of Dirac natural way to get an overall small size. Okay, so just to conclude, I'm over time, but what are we doing here? So what was the theme? The theme was an algebra between higher symmetries, like one-form symmetries, and ordinary symmetries. That was something that was kind of novel, that allowed us to see some new effects. And so we got some interplay between local operator deformations and dynamical charge particles. Those are the two different. Local operator deformations are things that would like to violate zero-form symmetries, and dynamical charge particles are things that would like to violate one-form symmetry. And optimistically, symmetry is the way, old school, to understand questions of naturalness. And I'm hopeful that perhaps these new ideas can give us some view on old problems in phenomenology. Okay, so I'll stop here and take 4 minutes.
I don't know who's chairing it, so questions?
So it's specifically regarding the, neutrino masses or, thermal masses more generally. If I had missed, the last few years of developments on symmetries and I didn't know anything about these non-invertible symmetries, but I only knew about the global symmetry structure and the anomaly.
I think you could have still discovered this model, but nobody did.
Right.
That's
kind of my question. It's like,
so you can think that I'm up here as an advocate. I am the higher Gruppenpest, to put the Wigner terminology on it. If you want to.
That's actually the Schrodinger.
Okay, yeah. Well, Wigner was the Gruppenpest.
Yeah, he was the target.
Yeah. Okay, I'm the Gruppenpest. So you could think maybe an analogy with quantum mechanics. If you're studying the hydrogen atom, nobody forces you to use group theory. You can say, I hate group theory. I'll just solve the equations and find the energy levels and nobody really forces you to do that, to use those tools. I think these tools are quite comparable. You know, you don't have, you know, in the end, what did I write down for, say, the neutrino masses? I wrote down a model of a Z prime embedded to SU3H, where I cooked up the matter in such a way that the neutrino mass was generated by instants. On the other hand, how did I discover that model? I discovered it by reasoning about the symmetries. So, you know, I think the tools are useful. And as more applications develop, I think the use becomes more apparent. But it's up to you whether you want to use them.
It'd be nice if there's, oh, sorry, go ahead.
But is there anything you could do without the group theory?
Is there anything?
Without the non-invertible symmetries?
Is there anything I could do without non-invertible?
You couldn't do without. So, for example.
But isn't that question answered by in the same way as the group theory example? Is there some physics problem that you are forced to use group theory to solve?
Oh, but I mean, you would hope that perhaps not in these examples you've given or that people have understood, but it's, you know, it's, one may imagine.
Well, but nobody, I mean, people have been writing neutrino masses for a long time, but nobody wrote simple instanton generating models of dirac neutrino masses. So, I mean, okay, where's the threshold? You know, maybe you think this is not it, but as more examples develop, I think it will be clear that we're able to see the structure of models more easily than without this tool.
I still have the same question. Then when you say instanton generated, you assume something about the UV. So there's the Wilsonian approach, declare a symmetry, and then you write everything compatible with the symmetries with coefficients of 4 to 1. So Wilsonian, Weinberg, Glashow, Gelman, it's this whole collection of ideas. Now, I think that you go beyond that, namely, you impose something on the effective action beyond what followed from ordinary symmetries. And the example with alpha H is kind of an example. You assume something about the high energy theory in the kind of terms that it generates.
Yeah, let's see if we can say that.
I think it would, I mean, I don't know that there's such a huge literature on this kind of stuff. I don't know all of it, but definitely the idea that there are symmetries that small parameters in the IR that naively are close to naive symmetries, be they anomalous or not, that you can embed into UV theories to make them legal and break them by exponentially tiny amount. This we've understood for 30 years, more probably. The question is whether we can really reliably estimate this tiniest possible size of the symmetry breaking effect. That's been the frustration all this time. Everyone has this argument, e to the minus some number over G squared. It's a monopole, lattice size of extra dimension, wormhole, whatever you want to call it. Everyone has some, has some kind of argument that gives you an answer roughly of this size. And it would be really interesting if there was some really specific number in front of it somehow. If it was more, we can make it bigger. I mean, in Nati's direction, we can definitely make it bigger. But things like U1s, it's interesting. It's hard to make it much smaller because U1s, we can't, they get weaker as we go to the IR. So we're talking about something like U1s. You could really imagine that something like e to the minus 2 pi over some alpha that you measure does give you a lower bound. You could get, but anyway, that would be really interesting if there's a more specific number.
Yeah, I would like to rephrase what Dima said. When you compute, say, mass of the eta prime, UCD, you use instantons off the low energy theory, and you know that there is no high energy term that can contaminate it. And there's good reason why there isn't. And therefore, the infrared computation is meaningful. For the others, it's not, because the term that you're trying to compute can get also contribution from hard terms that just happen to be there at short distances, and you assume that they're not there. Which is okay to assume it if there's some property of the low energy of the high energy theory that guarantees it, but it's not the rules have been you impose ordinary symmetry, cross out some terms, and then you compute the violation at low energies. And here, I don't see that symmetry. Is that consistent with what you? We came to a very conservative place today.
When I came here as a postdoc, I moved from, it was during bicep, and I moved from the center of optimism to the center of pessimism and correctness.
But Massless is not either, but truth. You moved to the center of truth in that case.
In the mid-80s, this with Harvard and Princeton.
Yeah, I don't have a sharp answer right now, but let me.
You can make this question, I can turn it around and make it sound positive. It's a clue. What should you impose about the short distance theory such that this reasoning will be completely justified? In other words, can you impose some kind of a non-invertible symmetry on the short distance theory that will guarantee that this reasoning is reliable?
I know how to. I know how to say something like that in the limit of zero coupling, but not in general. So, yeah.
So it's conceivable there's, I mean, for U1, it's conceivable there's an answer. I mean, if we think about plausible UV completions, it would all involve couplings that get stronger as you go into the UV. So it's possible that if you measure it, you know, you have a U1 coupling at low energy, it's possible there's a minimum possible size of symmetry breaking effect, e to the minus some number 2 pi over alpha at the scale, at your whatever low energy scale that you measure. That would be cool. That would be cool. I mean, it might be ridiculous. It's possible that it's it could be the size of a, I mean, if we're doing it in gravity, it could be the size of a black hole comparable to the low energy scale that you're at relative to the Planck scale. And one could even probably build models that give you something at that. Actually, I don't know about that. Yeah, all the simple models I know, they all do look like even minus some number of G squared, so it's hard to make it much more.
I don't know how, so should we write to you one? If we want to come to.
Yeah, please. Yeah, and we're meeting at 6:30 here.
6:30 done.
Yeah.
Okay, so I think we should thank Clay for a fascinating talk again.